So topological spaces is a very general notion. We start in the corner of sort of topological spaces arising from metric spaces, which are in some sense very special. We've discussed how compactness, we extracted that from a sort of reasonable seeming property of, well, let's say, a metrizable topological space. There's other conditions which are possessed by metrizable spaces which sort of make a topological space feel more normal, and the Hausdorff condition is one of those. You'll see in topology textbooks, including the one that I've recommended on the website by Munkres, statements like, basically every space encountered in mathematics is Hausdorff. Only analysts can say this. This is not really true. For instance, for algebraic geometers, none of our spaces are Hausdorff, essentially. Okay, so it's not the case that non-Hausdorff spaces are these wacky, insane things. That's not the case. But it is true that this is a very useful condition. So we're now going to develop briefly the theory of Hausdorff spaces. So I want to start with, before stating the condition, a simpler, so let's go back to the Sierpinski space, which was the first weird topological space we saw. Right? So it was the set 0, 1 with that topology. Now, why was it weird? Well, several reasons. I mean, one of which it's not metrizable. But perhaps the most obvious weird thing about it is that it has a point which is, perhaps doesn't even deserve the name point because it's not closed, right? So the point 0 is not closed. And whenever I say a point is not closed or is closed, I mean the singleton containing that point is not closed. Okay, I said this around the wrong way, didn't I? Okay, to say 0 is closed would be to say the complement, which is 1, is open, which is true. Okay, the point 1 is not closed because the singleton 1, its complement, which is the set 0, is not an open set, right? It's not in the topology. Well, coming from metric spaces, I mean, certainly you can see that every point in a metric space, if I take a different point, take an open ball around it, take the union over all the points away from my given point, that's an open set. So any point in a metric space is a closed set. Well, that's not true for the Sierpinski space, and it's a sense, well, that's one argument for why that's not metrizable. Okay, so there's a different question, which is, well, why could we believe perhaps in the meaning of points which are not closed? There is a good argument conceptually for that within algebraic geometry. This is not the time or place to give it, but there are reasons to care about non-closed points, but it's kind of subtle. So it is reasonable if you're talking about, say, manifolds or, spaces that arise in analysis, even if they're singular, that you'd want to consider only spaces for which points are closed. That's a reasonable thing to do. The Hausdorff condition goes a little bit further than that. Okay, so let me give the definition now. So space X is Hausdorff if for every pair XY of distinct points there are open sets U and V with X in U, Y in V, and U and V disjoint. Okay, there's really terrific mnemonic for this. So here's X, here's Y, and they are housed off from each other. Right, by the open neighborhoods U and V. Okay, so there's a whole range of axioms, starting with the axiom that points are closed, which is sometimes called T1. I won't spend much time talking about that. There's Hausdorff, and then there's a few others, regular and normal, which we'll discuss. Those are all called separation axioms, for the obvious reason. Right? The axioms tell you you can separate points. Okay, so that's the Hausdorff condition. What can we do with it? Well, let's first observe that it gives us that points are closed. Well, take a point. I mean, if there's no other points, then, well, X is the whole space, and the whole space is both open and closed, so we're done. If there are other points distinct from X, then take an open neighborhood UY. Take open sets uy and vy contained in X with X in uy and y in vy and uy intersect vy empty. That exists by the Hausdorff axiom. So there's X, there's y. So for each y, X is fixed and y is varying, and for each pair I take open neighborhoods, right? So there's y prime, that gets some other vy prime, and then correspondingly is some other uy prime. So that's uy, say, that's uy prime, vy, vy. Well, the union over all the y's distinct from X is open, and that's everything. Because it contains every other y. So it proves the complement is open, and therefore the point is closed. Okay. So at least in a Hausdorff space, points are closed. It's not the same condition, by the way. So having points closed doesn't necessarily imply Hausdorff. I'll briefly outline why this is true. Any metrizable space is Hausdorff. Okay, well, given, we choose a metric, let's call it D. Given 2 points in our space X which are distinct, well, if they're distinct, then the distance between them is positive, so epsilon is positive. Then U to be B epsilon X and V to be B epsilon Y suffice in the definition. That is, they're disjoint and they're neighborhoods of X and Y respectively. So they're clearly open neighborhoods. I just need to prove, and they contain X and Y, so I just need to prove that they have no intersection. And that's the case because, well, 2 epsilon, which is equal to dxy, is less than or equal to dxz plus d zy by the triangle inequality. So if z was in U, this would have to be less than epsilon. And if it was also in V, that would also have to be less than epsilon. So that there would be less than, strictly, 2 epsilon. But then I'd have a contradiction because I would have proved that 2 epsilon is strictly less than 2 epsilon. Okay? So, I think that's hopefully clear. Maybe I won't write the rest. That's, right, so a metrizable space is Hausdorff. Well, okay, maybe I'm going to do the example of a non-Hausdorff space. Well, here it is. Okay, so that's the real line, but it's got 2 copies of the origin. And I mean, I'll give you the full construction in a second, right? But think of the real line, and then you added an extra origin, but such that, you know, the points I'm pointing to with the chalk are close both to that and to that point, right? But these guys are somehow still not the same point. So in terms of their open neighborhoods, they're the same, but they're nonetheless distinct, which is why you can't detect the distinction between them by housing them off from one another by an open set. Okay, so how do we actually achieve this space? So this is often called the line with a double point. Well, I say it's a push-out. Right, so take the line R, remove the origin, so that's a subspace. Take the inclusion into R, take 2 copies of it, and then push that out. So what does that say conceptually? It says, take 2 copies of R and glue them everywhere where you take an image under these 2 maps. Well, that is, you glue everything except the origin. Right? So there's 2 copies of R. Let's call origin 1 and origin 2. So let's suppose, let's call this copy the first copy and this copy the second copy. And then, well, the equivalence relation looks like image of this is equal to image of that for every point there, right? So I'm going to identify, say, that point with that point, and so on, everywhere except for exactly at the origin. And, well, you can see how when I do that gluing, I end up with something. I mean, it's impossible to draw, obviously, in an accurate way, but okay, so that's a cartoon of what it should look like. So that is R disjoint union R modulo the relation. Well, tilde is the smallest equivalence relation which contains the pairs, well, let's say iota 1, iota 2. Iota 1x is equivalent to iota 2x, where x non-zero. Okay, but you can actually just see what that set of pairs is, right? So that set of pairs is the set iota 1x. Well, so if I want a relation on R disjoint union R, I just need to choose some notation, that's all, right? So iota 1 of a number x is something that lives in the first copy. Iota 2 of x is something that lives in the second copy. So I need to take all these pairs and I need to throw in any other pairs I need to get an equivalence relation. Well, I need that because it has to be reflexive. I need this because it's got to be reflexive. And then do the pairs that I've described have the right property to be symmetric. And, well, I guess I should throw in the reverse so that this is symmetric. And now everything here, it's reverse is also in the set. I have reflexivity, and I have transitivity. Okay? So that set of pairs is the equivalence relation tilde that I'm looking for. Okay, so if I take the map from the top left-hand corner to x either way, that sits every point which is non-zero inside x as either iota 1x, the equivalence class, or iota 2x, the equivalence class in the quotient. So that's a subspace. And the complement, so that's an open subspace, and the complement is just these 2 points. All right. So I've got to argue that there's no open neighborhood which separates these 2 points, right? Okay, so why is that? Well, an open neighborhood of O1, so by O1 I mean iota 1 of 0, right? Sorry, by O1 I mean the image in the disjoint union of one of the copies of 0, and then in the quotient those are still distinct because I don't see 0, 1 equals 0, 2 anywhere in that equivalence relation. Well, we can use the metric topology on R to talk about the topology we're using. And then if I take an open neighborhood of O1 in X, well, the pre-image under the quotient map is continuous. Well, the quotient map is continuous, so the pre-image is open. So it's an open neighborhood in the disjoint union, that is in this space here, of O1. Okay, so it has to look something like this. That's what you imagine, right? There's O1. I've got to take an open subset of the disjoint union which contains O1. Maybe you think that's sufficient, but no, this is the pre-image of something in the quotient. So if a point is equivalent to a point in the pre-image, right? So if I take a U, and then I look at rho inverse U, well, if I have a point in the disjoint union which is equivalent to a point which is in rho inverse U, well, their images are the same, so that point is also in rho inverse U. The pre-image of any open subset of the quotient is closed under the equivalence relation, right? It's stable under moving to points which are equivalent. Okay, so but look at that green colored in thing. Any point here, well, that's equivalent to the same point downstairs, right? So I'd have to have all of that stuff. And if I take an open ball, no matter how small, I must contain points arbitrarily close to O2. Okay, so that's the argument for why there can be no open neighborhood of O1 and an open neighborhood of O2 which are disjoint. There can be no neighborhood in X separating them in the sense of the definition. Okay, so X is not Hausdorff. In some sense, that's the typical way spaces fail to be Hausdorff, I suppose. It's worth also noting that, so maybe we'll prove it in a moment, the disjoint union of two Hausdorff spaces is Hausdorff. So the disjoint union of R with itself is Hausdorff, but the quotient is not. So in particular, this example shows that passing to a quotient doesn't preserve the Hausdorff property. Okay, so maybe I'll give you some of the reasons why the condition is useful. Well, if you're paying attention, maybe this bugged you a bit when we were discussing sequential compactness, because we knew for sequentially compact sets in a metric space that they were closed, right? So it seems a bit weird. I mean, compact seems to carry with it some implication of being closed, right? But in general, that's not the case. However, it is the case if the space is Hausdorff, right? Which fits with the metrizable situation, right? So in particular, in a metric space, a compact subspace, which is the same as a sequentially compact subspace, is closed, and that holds more generally for any Hausdorff space. Okay, and the proof is just this picture, basically. Okay, so given a k an x not in k, and a k, choose open sets UK and VK. Right, so the point here is that the x is fixed for the moment, and we're varying the k, and then we're going to take that cover of capital K. Right, so fix x, and then for every k, you choose open neighborhoods with the correct property. So k is in UK, x is in VK, and there's no intersection. All right. Well, then the union of all the UKs certainly covers k. Right? There's no requirement for UK to be contained in k. Okay, but since k is compact, finitely many of those will do. So say k is contained in U, I don't know, k1 up to U, kn. The n depends on x, but we don't really care about that. So k is contained in this finite union. Well, then x was in vk. I mean, k was varying over all of capital K, but now I can allow it to vary only over a finite set. And x is contained in the v's for all of those, right? So x is in the intersection of vk1 intersect vkn. And well, we're done. It's an open neighborhood of x, certainly. All right, so why is it disjoint from k? Yeah, I need one more piece of data though, right? That suffices to show that this open set doesn't contain any of the ki's, but I need it to not contain any k at all. Yeah, that's right. So I arranged for these ki's to be such that any k is contained in those. Yeah. So that's it. Right, because if k was in k, then k belongs to UKI for some I, right, because it's a cover. But then these guys don't intersect any of the UKIs. Well, in particular, that means k is not in VKI. right? Because I arranged for UK, I mean for any k, in particular for the KIs, UK and VK are disjoint, so there's nothing in common between UKI and VKI. So if k is already in this one, it can't be in that one. And if it's not in VKI, it's certainly not in the intersection. Okay, so that's it. So we produced for any x an open neighborhood which does not meet k, and therefore k is, well, the complement is the union over all of those. Maybe I should add that point. Okay, so, well, let's just write Wx to be the intersection of all those VKIs, right? That set there, that's an open neighborhood of x, and then well, x with k removed is the union over all x not in k of Wx, so it's open. All right, so that's useful. Compactness is better behaved if you're in a Hausdorff space. You know every compact subspace is closed. Okay. So here's a really useful fact. All right. So taking continuous map, where x is compact and y is Hausdorff. Then F is a homeomorphism. If and only if F is a bijection. Right, so one direction's clear, right? If it's a homeomorphism, of course it's a bijection because it has an inverse as a continuous map, let alone as a function. But the reverse wasn't the case. There was an exercise which asked you to check that a bijection, a continuous bijection, is a homeomorphism if and only if it's open, which is to say the image of an open set is open. That's not automatic. And if you've been doing the exercises, you know it's an immense pain to write down an inverse and then have to check some other completely new map is continuous, right? This is a great labor-saving device if you can show that the things involved are compact and Hausdorff. All right, so why is that? So, well, by the exercise I just quoted, I mean the reference is in the notes, it suffices to show, so we're doing this direction, right, that if it's a bijection and it's continuous and x is compact and y is Hausdorff, then F is a homeomorphism, and it suffices to show that the image of an open set is open. Well, why is that? Well, because that's exactly checking that the inverse function, which exists if it's a bijection, is continuous, right? Well, but x with u removed is closed. And it's a closed subspace of a compact space. And, well, there was this exercise I mentioned last time. It's straightforward to check that a closed subspace of a compact space is itself compact. All right, well, that's something, because we know the image of a compact set under continuous map is compact. Okay, so that's compact. Be a bit careful here. I'm not saying that the image of a complement is the complement of the image. I mean, that's not true. But I already know F is a bijection, right? So it's okay. right? I mean, just check the inclusions in both ways, because F is already known to be a bijection. This is a true state. Okay, so what have I shown? I've shown the complement of the image of U is compact. Well, but Y is Hausdorff, and a compact subspace of a Hausdorff space is closed. And therefore the complement is open. All right, so maybe that seems like nothing much happened, but if you've tried to prove maps are continuous by hand, you know how useful that will be. So the major remaining theorem is to prove that the finite CW complex is Hausdorff. We already know it's compact. That's going to be fairly involved, but it'll be a good test of whether we've grasped all the various parts of the theory of topological spaces. But I guess in the time I've got left, I'll just do one of these smaller statements. So let's prove that the Cartesian product of Hausdorff spaces is Hausdorff. So we take 2 points. So take 2 points of the product, and suppose they're distinct, then I might as well assume the first coordinates are distinct. So we may assume that x1 is not equal to x2. Well then, since x is Hausdorff, okay. I shouldn't have said that, because that makes it seem like I only need one of the spaces to be Hausdorff. Okay, so. Say the first coordinates are not equal. Then since x is Hausdorff, there are open u and v in x with x1 in u, x2 in v, uv disjoint. Well, then u cross y and v cross y inside x cross y are open disjoint neighborhoods of the 2 points in question. And if my 2 points happen to have first coordinates equal, well then, because they're distinct, the second coordinates wouldn't be equal, and instead I would use the fact that y is Hausdorff. Okay, so the Hausdorff condition is closed, well, in fact, also under disjoint unions, so under products, arbitrary products, in fact, disjoint unions, taking subspaces, not under quotients. However, nonetheless, although quotients are involved in the construction of finite CW complexes, we'll prove by bare hands that a finite CW complex is compact. And then, well, so what was the point of all that in some sense? The point is that the class of compact Hausdorff spaces, so these two conditions together, and you can see how they sort of, some of the interplay in that lemma. Well, this is often sort of taken as the class of good spaces. All right, everything works for compact Hausdorff spaces.